I'm Sujay King Liu, and I'm the Dean of the College of Engineering. On behalf of the College and the Department of Electrical Engineering and Computer Sciences, welcome to all of you. Thank you for joining us this afternoon for this IEEE Milestone Dedication Ceremony. It's a celebration. So my role here is really just to welcome you and to introduce the next speaker, Professor Emeritus William Kahan, and we know him fondly as Velvo. So just to say a few words, he earned his degrees all in Canada from the University of Toronto, joined the faculty there afterwards, but we were very fortunate to have him come to Berkeley in 1969 to join our faculty here in mathematics and in computer science. So we know him as the father of floating point. In other words, he played the key role in establishing this floating point computation standard, which was endorsed in 1985 by the IEEE and is used in all modern computers today. So I just want to say a few words. He has won many awards, very distinguished faculty colleague, and of course the Turing Award is probably the most prominent one, but he's also a fellow of the American Computing Association for Computing Machinery. He was elected to U.S. National Academy of Engineering. We are so proud to have him and to see him back here. I have to say my personal experience not working on the hardware side of the department, I've always enjoyed as a younger faculty member listening to Professor Kahan, because he would always attend our faculty meetings and have very thoughtful and very precise words to say. I think it's very apropos. So without further ado, I'd like to hand the microphone over to Professor Kahan, Velvo, for your remarks. Thank you.
When I started programming in 1953, the shadow of John von Neumann loomed over floating point. He said it was dangerously inaccurate and unnecessary because any competent physicist should be able to do without it. But of course, that didn't stop scientists and engineers from using floating point anyway. There were various difficulties with floating point because you could easily get very wrong results. It wasn't often that you noticed that. Usually you might notice that if you ran the same program, say a Fortran program in that era, if you ran the same Fortran program with the same data on different computers, you were likely to find disparities. And if you found these disparities, it would raise some interesting questions, like which if either of them was correct. I can recall an occasion when NASA developed a program to compute the deflections under launching loads of a space vessel. And they had to develop it on a workstation because the Cray was too expensive to use for development. They used it for what you might call important jobs. And then they ran the same program with the same data on a Cray 1 and on a Cray 2, and they got distinguished distances among the results. I mean, really quite different. Of course, which, if any of them, is correct? Well, it turned out that the workstations used our IEEE standard arithmetic, and so they got the correct result, as it turned out later. And the Crays got different results because of idiosyncratic rounding in the multiply circuits, different on the Cray 1 than on the Cray 2. Now, that was a symptom of the response to von Neumann's claim that floating point was dangerously inaccurate. Well, if floating point is inaccurate, then you might as well throw in a few more inaccuracies. They won't get noticed as if you can go faster. And so that's what poisoned the well. Now, it wasn't enough to try to get a standard so that people getting two machines conforming to the standard, running the same program, using the same capabilities on both machines, starting with the same data, should get the same results. that isn't altogether satisfactory, because what that does is obscure the fact that maybe both results are wrong. And that was a problem that we had to consider when John Palmer at Intel commissioned me to design a floating point for Intel's processors for what was to become the 8087, to become a companion to the 8088 and 8086. He wanted, he said, the best possible floating point for a vast market. Vast. How big? Well, he wouldn't tell me. I got a clue when a few months later, we had started to design this thing and figured out how to do it. He told management that he would be willing to accept no salary, provided they gave him $1 for every 8087 sold. and that gave me an idea about the size of the market. But what's more important is it was vast. Now, at that time, every computer used in scientific and engineering computation came with a local numerical analyst, error analyst, who might be helpful if the engineers or physicists or chemists program looked a little bit wrong or got suspicious results. That raised an interesting question. If we have a vast market, do we need a vast number of error analysts? And where would we put them? And as it happens, there aren't jobs, steady jobs, for a vast number of error analysts, because in industry, once the error analyst does his job, he produces a program which may be used for months or years, and then he's got to do something else. So error analysts, for the most part, would have jobs in universities, not all universities. And we don't have a vast number of universities, at least not as vast as the market for computers. So it was necessary to design the hardware so that you could live without the necessity to consult an error analyst, except in the most unusual circumstances. That was the challenge. And that's what leads me to the theme of my talk. It's a military maxim. Maybe it goes back to Napoleonic times. In every army large enough, there is always somebody who doesn't get the message, or gets it wrong, or forgets it. What is the message? The message is you should try to compute with extraordinarily, extravagantly more precision than you trust in your data or want in your result. Twice the precision would be enough, but even 3 decimal digits or 11 extra bits is often good enough. But if you do that, then it is extraordinarily unlikely that you will ever have to get the help of an error analyst. So the hardware designed for the Intel chip had 3 formats. One was single precision. That's about 4 bytes wide. And another is double precision. That was 8 bytes wide. And then there was a third, which was designed to be at least 10 bytes wide, but to grow. We expected it to grow as the speed of arithmetic on chip gradually came to go, instead of slower, a lot faster than access to memory that's off chip. Now, it's true with caches and so on, you can sort of buffer that thing, but still, it takes a long time to fetch the memory or to store it compared with the time to do floating point now. And we were looking forward to that day. And so we designed the Intel chip to have these three formats, the third capable of growth. And then when I spoke to Motorola in Austin, Texas, it was mid-1980s, they got the message, and they designed the 68,000s floating point, ultimately the 68040, with the same architecture. Every floating point register was extraordinarily wide. And that was used in Macintoshes for quite a while. I have a compiler that runs on the Intel 387, which has this architecture, running under DOS. Remember DOS? And I have a Fortran compiler that runs on the Mac Quadra, running under operating system 8.1. Of course, if you have a laptop, it's got operating system 13 point something or other by now. But 8.1 is the last one that works with this architecture. And they're a dream to use. It's such a pleasure to use those schemes because I don't have to worry about error analysis, even though I could do it. But I just don't worry about it. Alas, the message has been lost. It was lost early in 1980 when we went to Redmond, Washington, to discuss the support for the 8087 with Microsoft software engineers. And we were getting along just fine until around 11:30 in the morning. Bill Gates strode in and said, "Look, you see this socket?" It was a socket for an 8087, but empty at the time, a socket in the IBM PC. He said, "You see this socket? Almost none of them will be filled. And so it's not worth our time going too far out of our way to adapt our programming languages to support the 8087. And so they never did get to support the third format. And then, while Apple was enjoying nice floating point on the 68040, the Pepsi-Cola man, was John Scully, decided to marry Apple to IBM to share their market using one of the most fashionable processors available from IBM at the time. That was what was called the PowerPC. But the PowerPC had not been designed for a general market. It had been designed for a very specialized market. And so, although it conformed to the IEEE standard, optionally, only two formats, not the third extra wide format. And so Apple had to revise a lot of their software and throw out some of it. And they have not succeeded in reinstating the third format. So that message got lost. And then BuildJoy. Now, BuildJoy was one of our products. BuildJoy designed Java to use only double precision, nothing else, for floating point. Ultimately, he gave in and supported both single and double precision, but he never had this language supporting a third format. And so, again, the message was lost. It's not surprising that Bill and Joy used to have a contemptuous attitude to anyone who disagreed with him. And he really avoided the floating point people at Sun at the time. And so he just didn't get any advice from them. So now we have a situation where we're getting reproducibility. We're able to run software and get the same results on different computers, running the same language, the same program, the same input data. But we still have to worry about whether those results are correct. Too bad. Okay.
And it's my pleasure to introduce Kathy Hayashi, who's here representing IEEE. And Kathy's the director of Region 6 of IEEE, which covers 10 Western states, and she's on the IEEE Board of Directors, a real poobah. She's been in the semiconductor industry forever and is at Qualcomm at the moment, and we're very happy to have you here.
Well, thank you very much. It's a pleasure to be here. And IEEE milestones are important, and I am so honored to be here. And on behalf of the board of the IEEE Board of Directors, to be able to present this milestone here at UC Berkeley. Milestones are important for several reasons, and it's important for the university, and it's important for the community, and it's important for everyone to look back at the amazing innovation that has occurred here, and also to inspire those that will be walking through this hall and be looking at that milestone. And I hope that they remember, the people that were here before, the amazing innovations that have occurred, and I hope they're inspired because they are the next generation. And there's enough room for some more milestones up there. And I hope that the students will be there, and I know they will. And I hope that we can recognize all of their contributions. I hope that you all know about IEEE. It's one of the largest nonprofits supporting technologists around the world, and we do it in support of humanity. And we do it through many ways. We do it through some things you may have heard as our conferences, our events, our papers, but we also have a historical society, and that's where this comes from. And IEEE started, let me get the year right, Brian. It was in 1884 when IEEE started. And this milestone program started 100 years later in 1984. And so we are almost going on 40 years of presenting these milestones. And to me, this milestone and what we're recognizing today is important. It's significant, it's important, it's affected all of us. And I hope that we are able to show this milestone to everyone, and we applaud the milestone and the achievements that it represents. So without further ado, I'd like to also introduce from IEEE, Brian Berg, who is an independent consultant. He was specializing in flash memory, and he is a member of the IEEE History Committee, which is so important in bringing these milestones to us. He has served as the advocate for the 754 milestone to help ensure its approval. He's been involved with over 24 IEEE milestones since 2010. And so Brian will be presenting a little bit more about the details of the IEEE milestone program, which I encourage you to find and think about other milestones that might be in your area. And I hope that you will consider writing a proposal, and you can work with Brian on milestones, because we certainly do want to recognize as much as we possibly can. So thank you. Without further ado, Brian Berg.
Thank you. Thank you very much, Kathy. So it's a pleasure to be here. I was in this room 8 years ago when the dedication of the RISC processor architecture was dedicated. Dave Patterson led that effort starting in around 1980. And interestingly, when this plaque was dedicated, the next day another plaque was dedicated at what used to be Sun, what was then Oracle, for the first successful implementation of RISC architecture in the Sun Spark chip. So this plaque here was, the RISC was 152nd in the world, and the next one for RISC was 152 and Spark was 153. The one we'll be dedicating today is the 234th milestone. So Kathy talked a little bit about milestones, and I've been involved with them. I meet cool people and have fun when I do this. I've been involved with so many different kinds of milestones. It's a fascinating area. I'm really fascinated by history because obviously when you look around you, we're just standing on the shoulders of so many other people that are in various areas of technology and otherwise. Just wanted to tell you a little bit of background about some of the really interesting ones that are out there. I started thinking about, okay, this is a standard. I was wondering, is this like the first milestone that's honoring some standard? I was thinking, well, maybe it is. And then I realized, heck no, there's a whole lot of other standards that have been honored by other milestones, IEEE and otherwise. Just a few examples are, there's a dedication event I was at in Glasgow, Scotland back in 2018 for the standardization of the ohm. There's a really interesting story about that. They would actually, they were putting transatlantic cables down, even in the 1860s, bizarrely enough. A lot of people don't realize that. And then when they put one down, they blew it out because people could not come to an agreement on what an ohm was. So here's all this money spent, out the window or under the ocean or however you want to call it. And there's other milestones right here in California over in Folsom, the Folsom Powerhouse. If you're going up in the Sacramento area, you'll see a sign by the side of the road for a California Historical Landmark. Now there's also an IEEE milestone there. It was the first three-phase, 60 hertz, long-distance transmission center. So that's another interesting one. There's one for color TV. It was RCA in Princeton, New Jersey. The first atomic clock, 1948, the National Bureau of Standards. Ampex video tape recorder in 1956 with the analog video standard. So there's many standards out there. Standards are really, they're so critical to everything that we do that, that's a big part of it. Kathy was with me in Utah in late March for a dedication of a milestone for all the computer graphics works that has been done at the University of Utah. That was a fascinating event. It was a 2-day event. It was honoring the fact that Evans and Sutherland had come together and using ARPA funding. 1965, if you recall, ARPA was created after Sputnik freaked everybody out, realizing we got to get a bunch of engineers in this country or we're going to lose to the Soviets in the space race. 1957, so ARPA was started and ARPA did a lot of amazing funding, and we are here today doing this because of the legacy of ARPA. But what ARPA did in 1965 is they gave money to create what was called a Center of Excellence for Computer Graphics. This is before the word computer and graphics were hardly even used together. So the whole concept of that came from work initially done amongst other people by Ivan Sutherland with his PhD thesis for Sketchpad at MIT in 1963. So he came to Utah in 1968 and incredible things happened. Some of the graduates included people like John Warnock, co-founder of Adobe, and there's a really interesting story about his creation of PostScript language. It's the foundation of PDF files that came out of that. Ed Catmull, co-founder of Pixar with Alvy Ray Smith, who was also involved with the dedication event, and all the things that led up for the first fully computerized full-length motion picture, Toy Story in 1995. So all the legacy that led up to that started with the work at Utah. So it's a fascinating story. If you go online, we've got a video about that, of the dedication event. Anyway, so like I say, I get to have fun and meet cool people at these events and learn a lot of really interesting things. So what we're going to be doing a little later is we're going to be reciting the words of the plaque. Now, if you look at those words, the limitation is like about 70 words on a plaque. So the art of it is to create the essence of what is being honored so that both technical people and lay people can read those words, understand them, and appreciate the gravity of what's being honored. So I think we've done that very successfully. I really want to applaud the people I work with, Jerome and other folks, on this, because they came up with words. I only had very minor changes. I've gone through some major changes that other people just kind of throw some words together and, you want to do it right. It's so important to do it right because these words will be up here for decades, if not longer. So it's just a pleasure to be here. This is the importance of the IEEE History Committee and Milestones to be able to honor these accomplishments. And I'm looking forward to potentially another plaque for RAID, because RAID was done by way of Dave Patterson and 2 other people. They did not do the original RAID, but they did the most successful version of that. So that's another thing. You want to craft the words so that you're not saying too much. You don't want to say more than what actually happened. You want to record history accurately. So I plan to have a project with Dave Patterson at some point in the future for a RAID plaque. So maybe there will be a 3rd plaque up here at some point in the future.
There's more in the works.
Oh, yes, yes. I didn't even see you there, Dave. Hey, well,
We have more innovations than leaf plaques, I hear.
we can talk offline about that. So I'm pleased to introduce our next speaker. Dr. Demmel is Professor of Math and Computer Science here at UC Berkeley, where he's also former EECS Department Chair. He first came to UC Berkeley as a math graduate student in 1978, and his PhD advisor was Professor Kahan, who convinced him to switch to computer science and begin working on the IEEE 754 standard. Take it away.
So thank you very much. It's really an honor to be here. So when I started working with Belleville as a graduate student on the IEEE standard back in the late 70s, I didn't realize that I was signing up for over 4 decades of work. And in fact, I'll tell you a little bit about the last IEEE Floating Point Standards Committee meeting that we had on Monday. So it's not over. So if you read the history of the political obstacles that the first IEEE Standards Committee had to overcome, one of the biggest ones was how to overcome exceptions, in particular underflow, when the numbers are too small to represent. So the original proposal, called KCS, after Kahn, Koonin, and Stone, all the co-authors who are here today, it took several years to convince all the doubters on the committee that gradual underflow, as opposed to the obvious way just return to zero, flushing to zero, was a good idea. But fortunately, the committee members managed to recruit some outside supporters like Pete Stewart of Maryland, and Donald Knuth of Stanford, and Jim Wilkinson, so Turing Award winners, who weighed in support of this for mathematical reasons, as well as our own Dave Patterson and his student George Taylor, who's here today also, because what George did was he built a hardware implementation of gradual underflow while he was a graduate student that was just as fast as the one on the DEC VAX, and the DEC folks were the main objectors. And that sort of overcame the last objection that it was too slow to get the right answer. So as I mentioned, Floating Point is continuing to evolve. And so there's a new committee, which as I said, just met last Monday, which is all about 8-bit arithmetic. Now, I'm sure Belleville will have objections to 8-bit arithmetic. If you want 10-byte arithmetic is what you think is the right thing to do. But I'm very happy to say, and why is 8 bits enough? That's all you need if you want to tell dogs from cats or, where to place ads. That seems to be a lot of consensus on that. But the good news is that at the committee meeting on Monday, there was unanimous support for gradual underflow. So nobody is going to want to revisit any of those decisions that were made a very long time ago. Everybody agrees it's a good idea. And I was pleasantly surprised because when you only have 8 bits, every pattern is incredibly valuable, right? You only have a very small number of bit patterns to go around. But the committee decided that using them for these very tiny numbers was the right thing to do. And they're also keeping 1 or 2-bit patterns for nans, not in numbers. So there's still a debate about is it 1 or 2, but anyway, there will be nans. So getting back to the IEEE standard, it was already very widely implemented before the IEEE finally approved it in 1985. But that meant that the people who were building math libraries still had to adjust to all the different arithmetics that were around for a while. So I just want to tell you one story about my experience as one of the developers of LAPACK, which is a very widely used linear algebra library. And when we first brought it out in 1990, people were still using machines like those Crays that Belleville was telling us all about. And so what we had to do back then was put in we still had to be paranoid. We couldn't assume that all the arithmetic was doing it just the way the IEEE did. So we had a bunch of subroutines which call a routine called IEEE check, which does a few operations and comes back and gives you the likelihood of whether your machine is actually running IEEE arithmetic or not. And so just to mention one example, which is my favorite, and it's still in the library, and it still does it in all platforms because it adds a negligible cost, is that we have an array of numbers, and what we need to do is compute all the pairwise differences between pairs of numbers in the array. And so to make sure that nothing goes wrong, we take every number in the array x, and we replace it by 2x minus x. Now, 2x minus x shouldn't change x at all, and if you're in IEEE arithmetic, it won't. But on a Cray, it turns out what that does is it zeroes out the bottom bit of x. And that makes all the subsequent subtractions that we had to do accurate. And so anyway, that's the kind of nonsense that still lives in some of these codes. And I should say, anybody in the world who ever computes a singular value decomposition, it's in there. And so this is sort of a widely used thing, whether you know it or not. So as I mentioned, the 754 standard lives on, and it has to be reviewed every 10 years by the IEEE. Those are the rules. And the last version that we came out with was in 2019. And I just want to mention two interesting changes that we put into the standard. It does continue to evolve. And one of them was motivated by something that Belleville said that was a problem that was fixed. It's not fixed anymore, it's broken again. And that is whenever you run your program twice in a row in the same computer and hope you get the same answer, because how else will you debug, you can get different answers. And why is that? That's because computers are parallel. They're all parallel. And so if you're summing up a bunch of numbers, it may do it in a completely different order because it's faster. You'll get different round-off errors. And so this problem, and so who cares about that besides debugging? Well, lawyers actually care about that because if your program is saying this building will not fall down in an earthquake, the lawyers say it cannot change its mind when you run it again. So this is a serious requirement. And so this inspired many, many conferences at supercomputing meetings and so forth to figure out what to do about it. And so in the last IEEE standard, we added a new instruction. And I won't go into the details, but it does have the property that you can add up a whole array of numbers in an arbitrary order and get the same answer. And so that's one fix that we didn't anticipate back in the 80s. And the other thing is we fixed a bug. There was actually a bug in the standard that had been there for at least 1 decade, which is computing the min and max of two numbers. So I'll just let you imagine how we could possibly get that wrong. And it all has to do with not a numbers propagating correctly. So anyway, let me close by saying I hope we don't have any more bugs to fix in 2029, which is the next time we have to review the standard, and that exceptions are not going away. And what I like to do is, there's a video I like to show my students to motivate them to think about this. And Bora Nikolic found it somewhere online. It's about a robot race car that crashed into the side of the racetrack after one round. And there's a quote from the designer of that race car saying, "During this lap, something happened that apparently caused the steering control signal to go to Nan." So I hope all our robotics colleagues are paying close attention to this. So that's all I wanted to say. And at this point, I would like to pass the torch to my good friend, Jerome Kunin, who arrived 1 year before I did as a graduate student with Belleville. And it was his fate to uncover a bug in the PDP 1145 exponential function, and of course he went to Belleville to talk about it. And at spring break, Jerome was offered a mere 2-month project to write up the floating point standard that Belleville had a draft of. It took a little longer, and after 5 years, he went on to work on the Macintosh project at Apple. So let's welcome Jerome.
Thank you, Jim, for those kind words and for reminding us of why this is all worthwhile, right? It's a pleasure to be here. This is a big day for Floating Point. You can look around. You've never seen so many people gathered in one place to hear about floating point arithmetic. Belleville never hates. He's older than I am. He hasn't seen it either. I'm delighted to be here, and I feel with all these chairs and directors and professors, emeritus and otherwise, a dean. We have a dean with us. I'm here. I feel like I'm representing the emeritus graduate student, so that everybody has a voice. And look, I just have a couple of comments. The roots of the standard go back far before the 1977 founding of the committee. They go back decades into the mainframes and mini computers of the 50s, 60s, and 70s with their abysmal arithmetic. It was Professor Kahn who made it his business at Toronto and Cambridge and Urbana-Champaign and Stanford and ultimately Berkeley to work with his science and engineering colleagues to figure out what was going wrong with their numerical programs. He spent hours meeting many people around this. He alluded to the work with 3 colleagues to advise IBM on how to repair 360 arithmetic that had come out with some horrible flaws. They replaced the boards in the field and removed the worst of the anomalies. I'll have a drink when you're passing by too, by the way, but don't mind me. And one graduate student wrote to me about his work in 1964 up in Toronto to develop routines to handle over-underflow techniques that he was delighted to see 21 years later in the 1985 standard that we have before us today. Through this all, Kahn got an expert's view of what he wanted and didn't want in arithmetic. So that's one issue. Another is IEEE's tradition of principles above personalities. The society shies away from mention of people on plaques, and I think it's a good thing in general. Sure, if you coin Moore's law or if you found Shockley Labs, you get on the plaque, right? But the opportunity for error in bronze or the opportunity or omission in bronze makes it a good thing that we keep plaques relatively anonymous like this one. Yes, we have Professor Kahn here. I think of him as the godfather, not the father. And rightfully so, but it's worth looking at a number of people, several of whom are no longer with us, who helped pull this all together. What's so compelling about the IEEE standard is that at just that cusp in computing, as the transition went from big iron to silicon, at just that time, in a single stroke, this standard lifted the entire industry out of the horrendous mess that was the late 1970s and provided a powerful platform that would endure for decades, and as we've heard, motivates even arithmetic on tiny numbers done today. It just keeps on ticking. How can such an opportunity arise? It's a remarkable thing. And we can start with John Palmer. We've already heard his name. John Palmer joined Intel in 1976 with the mandate to do floating point for the 16-bit 8086 coming down the line. Palmer got his degree at Stanford under Gene Golub, whose pal Kahn from graduate school days would come across the bay to talk about numerical issues and computation. So Palmer knew exactly where to turn when he needed advice about what to do with floating point in 76. How was Kahn so conveniently across the bay and next to Silicon Valley? Well, we have Professor Beresford Parlett, who actively recruited him in 1969 as computer science was emerging as a department of its own. So he'd be here, not MIT or Carnegie Mellon or some distant place, not so amenable to work in Silicon Valley. So here we are in 1977. Kahn and Palmer are blazing away on the Intel 8087. Richard Delp of Signetics looked at a couple of early cut floating point chips from AMD and wondered, gosh, I'll talk to my pal Bob Stewart, the unstoppable Bob Stewart, the standards maven of IEEE at the time. Maybe there's an opportunity to standardize arithmetic in the microprocessor industry before the whole world goes crazy, as it has in the past in the minis and mainframes. Bob Stewart, the unstoppable, irrepressible, if any of you remember him, took little time to found Committee 754, installing Dick Delp as the initial chair. But finally, there's one more link, and happily he is here today, David Stevenson, who within a year or two took over the chairmanship of that Committee 754 and very deftly guided us through years of discussion about competing proposals. Discussion's a polite word. Competing proposals and science projects and all the other things that instigated by the appearance of a standards committee. He got us to 1985 in good stead. So any way you cut it, the threads that run through this are the experience, the insight, the perseverance, and the persuasiveness of Professor Kahn. And he applied that same diligence to his students and colleagues along the way as well. He taught us how to tune our cars, why we ought to be using electronic ignition, if those of you remember back that far. He taught us how to speak, how to write in that Dickensian style that he so enjoyed. He taught us how to dress. A few of us he helped find a mate. I think I did that. I think I went solo on that one, and got very lucky. But anyway, it's time to see what's behind door number one here. So without further ado, let me introduce gladly Professor Claire Tomlin, Chair of EECS, who's going to keep this ball rolling. Thank you.
Thank you, Jerome. And I get to do the fun part here, which is the toast. We are going to toast and simultaneously unveil the plaque. And it's going to be unveiled by three people. So Jim mentioned in his talk the spring break in 1978. No, I was 7 years old. I had my Commodore VIC-20. It was doing addition, subtraction, multiplication, division, and square root. Well, I think. But we have the three initials of the KCS proposal to Intel in 1978 are here. Velvel Kahan, he's the K. Jerome Koonin, who's the C, and Harold Stone is the S. And it's a great honor to be here and to ask you all to raise your glasses to toast this latest IEEE Milestone project. Thank you. Cheers. Cheers. And now, please grab a corner of the veil and we'll see the unveiling.
One, two, three, go.
What does it say?
Well, we will have the words. You want to come over here, Kathy? So Kathy Hayashi and I will recite the words of the citation, and we will present the plaque to the university. Oh, you go.
Let us know if there are more than 70.
In 1978, faculty and students at UC Berkeley drafted what became IEEE Standard 754 for binary floating point arithmetic. Inspired by ongoing collaboration with Intel, the proposal revolutionized numerical computing.
Its carefully crafted arithmetic and standard data types promoted unprecedented software reliability and portability. By 1980, microprocessor companies were already implementing the proposal. Once approved in 1985, IEEE 754 was widely adopted as the standard for robust numerical computing. On behalf of IEEE, Kathy Hayashi and I present this plaque to the University of California at Berkeley.
one thing. My name does not appear on that plaque, and for a good reason, because it really did take a lot of work by graduate students and other friends to get that thing done. Moreover, what is left off the plaque is that graduate students working here produced a math library, a library of transcendental functions like log, exponential, sine, cos, arctan, hyperbolic functions, and so on, which was very, very widely distributed with 4.3 BSD Berkeley Unix. And of course, that helped a lot for compiler writers to be able to use the library while implementing their compilation with that kind of arithmetic. So that's why I'm really glad about that, because my reward is that the thing is taken for granted now. That's what I wanted.
Bravo!
I have 6 words to say, and a little more. Now you see it, now you don't. What does that mean? Now you see it. Graphics, video. Do you realize that 65% of internet traffic is video? And that video uses compression and decompression, all with IEEE floating point standard. Now you don't. What's that? When was the last time you saw a floating point trap? I just heard about one recently. They're gone, just about. So now you see it, now you don't. That's magic. That's the standard.
Yeah, so thank you, Harold. We now invite you all to join us upstairs in the Wozniak Lounge, which is 1 floor up over on that side of the building, for some refreshments. Thank you very much.